Hello and welcome to video number 17. My name is Untitled. This video will show a proof of the even function test. Basically, we will start with linear functions and then we also prove the nonlinear case, and after that we will provide a general formula for a polynomial and show the condition that makes the polynomial an even function. To start with, for the linear function, our hypothesis: if the line L connecting these 2 points minus x comma L and x comma L for every real number x is symmetric about the y-axis, then f of x equal to L is an even linear function. Let's go ahead and depict what we just said. This is the x-axis and this is the line f of x equals to L. Since the line f of x equals to L, that means f of x is equal to L regardless of the parameter, which is any point in the x-axis. Any point in the x-axis, if we consider it as a point from the domain, then its range is the L, f of x equal to L. So the range, since the mapping is 1-to-1, the range must be identical to the x-axis. So the only difference between f of x equal to L and the x-axis would be the fact that x-axis is crossing at y equal to 0 and the line f of x crossing the y-axis at y equal to L. That's the only difference. So if that is the case, then we know that, let's go back to the hypothesis. If the line connecting the 2 points for every x is symmetric about the y-axis, and sure enough, from what we just mentioned, since the x-axis is symmetric around the y-axis, we know that the line f of x equal to L is just the image. It's just like a mirror image of the x-axis, so it must be symmetric around the y-axis, and that's what we have here in the hypothesis. If it is symmetric around the y-axis, there is a theorem in calculus that says if a function is symmetric around the y-axis, then the function is even. So this line is an even function, and it's also a linear function, because f of x equals to L, that means this function has no term that depends on x. So any changes in x is not going to change f of x. So that wraps up this part. Let's go ahead and use the theory to prove what we depicted over here. So theoretically, we can say the fact that the function f of x equal to L implies its slope is equal to 0, because the derivative of both sides will give us 0 on the right hand side. Okay. Thus the line L is parallel to x-axis, and every point on the x-axis has an image on the line L. The second point is that since the y-axis bisects the x-axis into even halves, it follows that the function f of x is a linear function because it is a straight line. Also, it follows that f of x is an even function because it is a symmetric function. It is symmetric about the y-axis. It's just an image of the x-axis. Since x-axis is symmetric around the y-axis, then its image, which is f of x equal to L, is also symmetric around the y-axis. What is our conclusion? Our conclusion here is that f of minus x is equal to L, f of x equal to L, f of 0 equal to L, f of any number that is real equal to L. So since f of minus x equal to L and f of plus x equal to L, the right hand side for both equalities equal to 1, that means f of minus x equal to f of x. That proves the first part, which is for the linear function. Now we will use the linear function to prove the nonlinear case. Let's take a look at the nonlinear case. The nonlinear case, our hypothesis will be for the line Li connecting 2 points. This is just like the same line for the linear. So this is the linear case. For every x in the domain of a function f of x is bisected by and is perpendicular with the x-axis, denoted by L, which is the line PP perpendicular to the y-axis, then f of minus x is equal to f of x. If we recall just now when we were talking about the linear, we said the line connecting this point, these 2 points, for any value of x, this line is linear and is symmetric around the y-axis. So that means this line is bisected by and is perpendicular to the y-axis. So since that is the case, then f of minus x will be equal to f of x. Let's depict this one, and we have the function f of x, which is a nonlinear function. And if we trace it, it's just like an upside down hat. This is our function f of x. We want to prove that this function passes the test for the even function test. It passes the even function test. But we're not going to work on the function. We're going to work on just 2 points and the line connecting them. And since this will apply to any 2 points, an image, and it is object, if we consider y-axis as a mirror, since it applies for all, then we can prove that f of minus x equal to f of x, and the function f of x satisfies the condition for the even function. So let's go ahead and use theory to prove the hypothesis. Proof. We said since the line L is perpendicular with the y-axis for every x in the domain of a function f of x, then the slope of L, the line, we're talking about the line, not the function, the slope of the line is given by m equal to y2 minus y1 divided by xi plus xi. Let's go back to the figure to just point out this. If we look at this, we want the slope of this line. To get the slope of this line, we can say y1 minus y2 in the numerator divided by xi minus xi in the denominator. And that's what we're talking about here. So m will be equal to y2 minus y1 over x plus xi. Now one point that we have to emphasize here. We said the line L is perpendicular with the y-axis. But we know also the x-axis is perpendicular with the y-axis. That means the line L must have slope equal to 0. So the slope equal to 0, what does it imply? Implies that y1 is equal to y2, since the denominator cannot be equal to 0. So m equal to y2 minus y1 over x plus xi implies L is parallel to the x-axis and y2 is equal to y1. Second point, the line L is bisected by the y-axis, and this is what we have done for the linear case because we're talking about the line. Okay, so the fact that it's bisected by the y-axis implies the distance between the object, which is xi y1, and the image of the object minus xi y2. The distance from each of them relative to the y-axis is the same. So if we do this, the distance between xi and y1 to the y-axis is the same as the distance between its image minus xi y2 to the y-axis. And this applies for every x in the domain of the function f of x. What good will that do? Here is the conclusion. We concluded over here that y2 is equal to y1. But we know also y2 is equal to f of minus x. y2 is equal to f of minus x. This is minus x, so this is f of minus x. So y2 is equal to f of minus x. And we know y1 is equal to f of x. Here is x sub I, and here is f of x sub I. So y1 is equal to f of x sub I. So if that is the case, we know that y1 is equal to y2. So the left hand side of this equality, which is y2, equal to the left hand side of this equality, which is y1. Since y1 is equal to y2, then the right hand side of both must be the same. That means f of minus x must be equal to f of x. And that's what we want to prove for the nonlinear case. Remember, we did not use the function f of x to prove that it is linear and even function, because f of x is not linear. When we talked about the linearity, we're talking about the 2 points that are on the function f of x. One of them is the image and the other one is the object, and the line connecting them, we call it L, and that line, we prove that that line is symmetric around the x-axis. And from that we concluded, since that line could be moved up and down as long as the points are on the function f of x, then the function f of x itself is an even function. Now that we've done this, let's move on to our last part of this video, which is about the polynomial function. So the polynomial function, we can have a general formula for it. The general formula we have here, f of x is equal to a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 plus a sub n minus 2 x to the power n minus 2 plus dot 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 plus a sub 2 x squared plus a sub 1 x plus a sub 0. Here is our statement. The function f of x, which is this function, is even if and only if a sub z equals to 0 for every odd number z, where z between 1 and n, both of them included. What does that mean? We have the coefficient of x to the power n, which is a to the n. So a to the z is a coefficient. So what we're saying over here is that the coefficient of all the x terms where the exponent for x equals to an odd number, the coefficient will also be odd number, and we want that coefficient to be equal to 0. Why? Because we do not want to see any term with an x that has exponent that is an odd number. That means we just want f of x to have terms that have x's but with even exponents, and they could also have the constant term, because x to the power 0 is not an odd term, so we could have also the constant. So here is an example to demonstrate this. This example shows a function that has only even exponents for the terms that have x. So let's go ahead and apply a test. To apply a test, we cannot use every real number. We can just use one real number and we can generalize it, because it's just an equation that's proven to be correct. So let's go ahead and plug in 1. If we plug in f of x equals to 1, we know that we plug 1 here, we have to plug 1 over here. So 2 times 1 to the power 4 is equal to 2, plus we have 3 times 2 to the power 1, 3 times 1 to the power 2, 3 times 1 to the power 2 is equal to 3, plus 7, so it's equal to 12. Now we will go ahead and plug in, instead of x, minus 1. If we plug in minus 1, then we will have 2 times minus 1 to the power 4, which is equal to 2, plus 3 times minus 1 to the power 2, which is equal to 3, plus 7 equal to 12. So since both of them result in 12, then f of 1 equal to f of minus 1. And since 1 is just general random pick, then if we pick any real number, regardless, this equality will be satisfied. And that proves that such polynomial is an even function. Let's take a look at another example, but in this example we have one term, and this term that has x with an exponent that is an odd number. If we do the evaluation, f of 1 equal to 1 will be equal to 2 times 1 to the power 4, which is 2 right here, plus 3 times 1 to the power 3, which is 3 times 1, which is positive 3. So we have it, plus 7 equal to 12. But then here is the difference. If we plug in minus 1 here, then we will have 2 times minus 1 to the power 4, which is equal to 2. But 3 times minus 1 to the power 3 will give us 3 times minus 1, which is minus 3, so negative 3, plus 7, and that will give us 6. So the results are not equal, and that means f of 1 cannot be equal to f of minus 1. And that proves that this function is not even. But what comes to mind is, if it's not even, is it odd? And that function may even not be equal, may not even be an odd function. And that will be demonstrated in a video that we will publish next week. Let's get our conclusion. A function f of x will not be even if the power of at least one of its terms, that is the power of x, for at least one of its terms is odd, then the function is not going to be even. Such a function may not be odd too, as we said. We hope you enjoyed this video, and thank you for watching. Please subscribe to our channel. We will have more interesting subjects to come. You have a good day and stay safe.